week I had the nice surprise of getting two new solutions to problems which I exposed, so I'm very happy of this, and it's good that you get solutions, but it would be that somebody gets solutions, but it would be much better that everybody tries a solution, okay? So please, do try. If you don't succeed, I explain, you understand. You don't try, I explain, you don't understand. So please try. Okay, let's go to cycles. A walk is closed if it has positive length and its origin and terminus are the same. A closed trail whose origin and internal vertices are distinct is a cycle. So a cycle is almost a path. The only difference is that origin and terminus coincide. So apart from the origin, which is equal to the terminus, all other vertices are gone through just once. Okay. Just as with paths, the authors use the term cycle to denote also the graph corresponding to the cycle. Okay. A cycle of length k, so with the k edges, is called a k cycle. A k cycle is odd or even according as k is odd or even. A 3 cycle is often called a triangle. Okay. And here you can see a closed trail, okay, and also a cycle. And now, bipartite graphs are rather important, as I already told you, in various graphical expressions, combinatorial expressions, or situations in which you have a relation between objects of different nature, okay? Teachers and classes, such things, men, women, or, okay? Producers and users and so on. Okay, so bipartite graphs often come up in interesting practical situations. So the definition is the definition, but here we have an interesting characterization of bipartite graphs. I think I already told you. I'll tell you various times my mantras, my ideas, recurrent ideas. Necessary and sufficient condition, something which is so if and only if it is so, is interesting meta-mathematically. Why? Because on one side you have what you're interested in, but you might have the difficulty in finding. On the other side, there is something which by itself seems not to have any interest for you, but which is computable. Okay, my typical example for my freshmen, I teach at the first year of the 3 years degree. Okay, and so I teach linear algebra, and the typical example is what is called the Rouchet-Capelli's theorem, which says a linear system has solutions if and only if the rank of the incomplete matrix is equal to the rank of the complete matrix, which is the one given by the incomplete matrix with the addition of the column of known values. Okay? And on one side you have something you are interested in. To know whether that system has or does not have solutions. And you don't see a possible solution, so you would like so much to have someone to tell you it has solution or it has no solution. On the other side, there is something which you can compute because it's boring, it's nasty, but you know how to compute the rank of matrix, and so you can compute the rank of the incomplete, the rank of the complete. But who cares? Doesn't tell you anything. But you have this logical bridge which says, okay, if and only if. So what you are interested in is completely decided by what you can compute. You have no interest in computing those two ranks, but you know how to do. You are interested in knowing whether the system has solution, but you can't see it directly, and so you can have this. So there is the notion of bipartite graph, which is the one I already gave you, the possibility of splitting the vertex set into two subsets, disjoint subsets, x and y, so that each edge joins a vertex of x with a vertex of y, and consequently no two vertices of x are adjacent, no two vertices of y are adjacent. This is the definition. But how could I try to see that it is bipartite if the bipartition is not as clear as in the first example you saw, where you had x 3 vertices here, y 3 vertices there. Okay, how can I know? By this condition, this necessary and sufficient condition. A graph is bipartite if and only if it contains no odd cycle. And this, as very often in mathematics, almost always in graph theory, is very easy on one side, it's more difficult on the other side, okay? But it's rather natural like that, because sometimes you have a sort of slowing down of information, and so it's difficult, like a salmon, to go up the flow. Okay, let's see. First, we assume that G is bipartite, and let's see that all cycles must be even. Okay, so you have a bipartition, x and y, and take a cycle, V0, V1, Vk, V0. Okay, now you can assume that V0 belongs to the set X of the bipartition. Okay, but then you have V0, V1, which is an edge, and so it must join together V0, which belongs to X, with some vertex V1, which belongs necessarily to Y. Otherwise, it's not bipartite. Okay. After that, what about next vertex? It must belong again to X. Otherwise, you would have that the edge V2, V3, V1, V2 connects two vertices of the same set, which is not possible, since we know by hypothesis that it is a bipartite graph. Okay, so each time that you do two steps, you are coming back to X, okay? And if you had, and each time you are doing an odd number of steps, you are going from one set to the other. So you cannot have a cycle. A cycle comes back to the original vertex, so comes back to X in our case. And so it cannot be odd, because it would have as a final vertex a vertex which is in Y. But it's not possible, because you're coming back to the original vertex, which is, of course, again in X. So it's very easy to prove if the graph is bipartite, then all cycles are even. The more difficult part is if you have a graph in which all cycles are even. Can you deduce a bipartition? Yes, it's possible, and it's what I'm going to prove now. And let's see what's the problem. The problem is, in a sense, similar to the problems we have met so far with walks and paths, okay? But with particular, we'll see. Okay. So now I give you the candidate bipartition. So I give you two sets of vertices. We are starting with the connected graphs anyway. So I give you two sets of vertices, and we'll see that actually they build up a bipartition in the correct sense. So how do I build the two sets of X and Y? Choose an arbitrary vertex U, okay? Any vertex U. We fix it. And then we put in capital X all those vertices such that the distance from u to x is even. And in y, all the vertices of v whose distance from u is odd. Is that a correct bipartition? How could we know? We take two vertices in the same set x, and let's see that it's not possible that these two vertices are adjacent, so that there is an edge between them. Okay? If I can do that, then I'm done. Actually, this is, and I can do the same thing for y, of course. But it's the same argument for x and for y. So what I like to do, I repeat, what I have to do to show that x is a good part of a bipartition, I have just to show that if I take any two vertices in x, there is not an edge between them. Okay? Are you with me? Okay? Just by the definition of bipartition. What is a bipartition? X and y sets of disjoint sets of vertices such that no two vertices of x are adjacent, no two vertices of y are adjacent. Okay? So this is the set x, this is the set y I define by starting from a particular but totally arbitrary vertex u, and then I prove that if I take two vertices v and w in x, then there is no edge between them. How can I do that? We have a shortest uv path from u to v, okay? And I have a shortest uw path from u to w. They both belong, v and w, they both belong to x, so these two shortest paths are both of even length. Are you with me? Okay. Now, what do we have? No problem if these two paths have no vertex in common, okay? But it might not be so. It's exactly the same type of problem we had half an hour ago. So, if I have vertex u, vertex v, and I have such a path, vertex w, and I have such a path, p and q, absolutely no problem. Why? Because I can have a path from if I had an edge between v and w, then I would close a cycle of odd length. Why? Because this is even, so all this is an even number of edges. If I had also this edge between v and w, then it would give us even plus 1, an odd cycle. But our hypothesis is there is no odd cycle in the graph. Remember what the hypothesis is. But it's not, life is not so comfortable as it is here. You might have that you have u, you have v, and you might have that your path p intersects path q, meaning that I might have something like this, and this is path P, and I have oh, sorry, I have to go to W. Okay? I might have something like this, that these two shortest paths from U to V and shortest path from U to W, they meet at some point. Even more than one vertex, okay? But then what they say is just take, call U1 the last vertex which is common to both. So you might have, they intersect, but call U1 the last one, which is of intersection between the two. So after U1, after in P, after U1 in Q, you don't have any more vertices. Again, I can say something like this because we are in a finite situation, okay? Now there is an interesting thing. What happens to the two sections of these two paths from U to U1? They must have the same number of edges. Why? It's written there, but don't look and try to think about that. The claim is these two sections, I've done that in my drawing, these two sections must have the same number of edges. Why? What are the assumptions, the initial assumption? What is P? It's not the path. It is the shortest path. Okay? And Q is the A short, there must be more than one with that minimum number. A shortest path from U to W. Then, why can I assert that the two sections of P between U and U1 and of Q between U and U1 have exactly the same number of edges? Yeah. Assume that we have something. I make a similar drawing, okay? But with something which I will say it's not possible. Why is such a situation not possible? No, you don't answer, please. But I would like also the other people to try to answer. Don't be shy. So, there are three possibilities. You answer and you answer the correct thing. Okay. You answer and you answer a wrong thing. Very interesting, because then we can analyze much better. You don't care. The third part is horrible to me. Okay? Why? Because you don't need an incredible background to do these things. Graph theory, at least in this moment of the course, is extremely not easy, it's elementary, which means you don't need a background. You just need to reason about it. So I don't think that you are not able to reason about it. I think that you might be uninterested. This is, of course, dangerous for your exam, but I don't understand. Please, try it. It's, you are here, since you have decided to be here in the classroom. You might be out. Nobody follows you and asks you to come in the classroom. You can. You're not compelled, okay? So if you are here, you have decided to try, and you don't need the background to reason on that. Why? I would like not to have always the lady, the gentleman and the terrible lady that Yeah, to always. Now, I like very much terrible lady. Okay, why? Why is the second thing not possible?
The lady would like to answer the question.
The terrible lady you can answer only after 60 seconds. Okay. What if you don't know? I understand. Remember, we teachers, professors, researchers in the university, we study still. It's a bit different from what happens in high school. We have to study because we do research, and doing research means that we have to study quite a lot. I studied all yesterday. All yesterday I had to study. Okay? And so I understand your difficulties. You might not be sure of what you're talking about. Then there is a solution. Go to the definitions. If you are in a proof, go to the hypothesis. If you have done a construction, go to the features of the construction. And so that's why I recall what are P and Q. They are assumed to be shortest paths from U to V, from U to W. Then, why is it impossible that this is the case in a situation like this, where here I have 2 blue edges and here I have 4 red edges? Why is it impossible?
They need to have the same length.
Why do they need to have the same length? Because if they didn't have, like in this case, who would be cheating? Who? No. This red would be cheating. Why? Because if you follow the red, take this as an example. What's the length of the red one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you might have what? Okay, I see the terrible lady who looks like saying, I would like to answer, but he does not allow me. Well, come on.
No, I don't know what the question is about.
Okay. Again, no, okay. Correct assertion. These 2 pieces must have the same length. So this is not possible. Why?
Okay, because the blue one has 2 edges, so it's the shortest path. So the red one is not the shortest path, which is on the contrary, you have to have.
Wait a minute. Which shortest path?
From U to U.
I never told anything like that. I am asserting that P is a shortest path from U to V, and that Q is the shortest path from U to W. This is what I said. Can you say that it's not true almost by what you're saying? What is wrong in what I've said? I'm saying that, listen, here you have vertices, okay? I don't know whether you understood what I mean, that these are all vertices, okay? So, what is wrong in what I have said? In this condition, I have said P is the shortest path from U to V, Q is the shortest path from U to W. What is wrong in what I've said? P? Why?
Because if I choose the other...
Because if I go like this, U, here, U1, and then go red, then I have a shorter path from U to V, which is almost it's concerning what you were saying, but I never said that it was a shortest path from U to U1. It's something you can deduce by the fact that these are shortest paths, okay? And then necessarily they must have the same. But just take, you have good ideas, but you must comb them, you know? You must comb your ideas, okay? Which means good ideas, but put them in the correct order. So I've never said that they are shortest path from U to U1. Try to see what I've said, which is not correct if I take in that situation. Okay?
Is there any implication that you have this shortest path that and we have the intersection UV1, then UV1 by T and UV1 by Q have to be shortest path?
Yeah, sure.
The fact that we have two shortest paths.
Sure. You have that as a consequence, okay? But it's immediate to say, I mean, it's what the Viterbo lady did, okay? Going through that argument. But it's more immediate if you say, I've said that P is the shortest path from U to V. It's not true. Why? Because I could compose a shorter path than P by taking that blue piece from U to U1 and then the red piece. Then it would be shorter, necessarily shorter than P. So it was wrong that P was the shortest path. Okay? All right. So this is not like this. But what about here? Are they even or are they odd paths on the same length from U to U1? No, we don't know. But it's not important. Why? Because it is the same number. So it might be an odd number in this case. Okay, sorry. Of course, here I did it even. But it might also be like this and like this. And then what you have is no problem if the number of edges from U to U1 is odd for both. Why? Because then what you have from U1 to W will be odd, from U1 to V will be odd. Even in both cases, even the pieces from U1 to W, even from U1 to V. But the important thing is that the two pieces from U1 to both will be of the same parity, either both even or both odd. But summing two odd numbers or summing two even numbers always gives an even number. And so again, if you had an edge like this, you would close a cycle, an odd cycle. Okay? In both cases, you would close an odd cycle. Why? Because this is the last intersection point between the two shortest paths. So you don't have any more repetitions. And so this would be odd plus 1, and this would be even plus 1. In both cases, an odd cycle, which is forbidden by our hypothesis. Okay? I would like you to remember this is graph theory as a subject, but not the exam, the course, is not graph theory. It is mathematical methods. And so I want you to adopt this way of reasoning in abstract way on finite things, on discrete and even finite things, which is not so common in what you've studied so far. Okay. So this time, try to show that if small delta is greater than or equal to 2, then G contains at least one cycle. Always think at least one when they say a cycle, translate it into at least one cycle. Okay? Now, let's go to something which is more engineering-minded. Okay? And it is a problem, an optimization problem. One of the most common problems which is in your navigator, okay, in the car. In a reverse way, but it's in your navigator. And it's called Dijkstra's algorithm. What's the problem? First of all, what's the problem? Then what's the solution? Okay? The problem is I have a weighted graph, meaning that on each edge I have a positive number, which we may interpret as length of a road from this town to that town. Okay? And what I have is that I want to build shortest paths from one particular vertex to all other vertices. We are in a connected graph, so okay. So if we are talking about railways, we shall stay on the continental Italy or in Sardinia and so on. Okay, and we can also have a different notion of distance in this case, in which you don't just count how many edges, but you sum the length of the edges of the path. Okay, and so you want shortest paths from one particular vertex to all others. Okay, what you have we'll see in the next chapter a slightly different problem with a slightly different solution, of course, in which I don't care about a particular vertex. This is one thing I will ask you in the exam. What's the difference between the problem of Dijkstra's algorithm and the problem of Kruskal's algorithm, which will be in the next chapter? Here, I want to optimize things for a particular vertex. In Kruskal's algorithm, I want to optimize things in an absolute way. Okay? But we'll talk about Kruskal's next time. Now, I have a privileged vertex. And this is very common for airlines. Okay? Which means if I am Air France, I don't want to have the shortest path from, say, Bologna to Copenhagen. Okay? What will I do if I'm Air France? I will take you from Bologna to Paris-Charles de Gaulle, and then from Paris-Charles de Gaulle to Copenhagen. Okay? Why that? Of course, for my time, it's worse. It takes more time to me, but it takes less to Air France to have just two lines from Paris to Bologna and from Paris to Copenhagen, instead of having a further line from Bologna to Copenhagen. Okay, and so you do that, and you do it. This is an international course. You surely have gone, I don't know, maybe you have passed a couple of hours in Doha, Qatar, or somewhere in Frankfurt or in Paris. Why exactly? Why? Because these networks are optimized for a particular vertex of all the net. Okay, and so think of having already a network of streets, and you want to program your ways from Bologna to all towns which are province towns in Italy, and then you can do that, and it will be centered on the idea I want to have the shortest from Bologna, not in absolute terms. Okay, this is the main difference. We'll talk about that further on. So what's the idea? Here there are long reasonings, but let's go to the algorithm itself. Let's go to the algorithm itself. Where is it? Here it is. Dijkstra's algorithm. Oh, sorry. You can follow here, but it's the easiest thing is to follow it on the example which is here. So you are starting from a particular vertex, in this case vertex U0. So let me repeat. This problem is centered on a particular vertex, okay? And it wants to make things best possible for that particular vertex, in this case U0. So we wanted to do two things at the same time. To find the distance, so the minimal distance, minimal route from the length of the minimal length of a route from U0 to every other vertex, and by doing that also to find the route itself. Okay, and it's what the navigators do the other way around, by taking your goal and using it as U0. Why? Because you might decide to take a different road, you might take the wrong turn, and so the algorithm must start again from your destination, finding all possible minimal routes, including the one which goes to where you are in that moment. Okay, there are quite a lot of tricks to avoid useless parts of this algorithm, but let's take the base algorithm, which is this. At the beginning, you are in U0, and the distance is 0. Okay. Then what do? You look around what is adjacent to U0. You just take the vertices which are one edge apart from U0. And so you have this edge, this one, and this one. So you have 5, and you look at these 5. And you take what? The edge will mean an edge, if there are more with the same length, with the same weight, with the minimal weight. Okay, so I have weight 1, weight 2, 8, 4, and 7. So I take 1. Okay, and I can immediately say that this vertex is at distance 1. All right, so now I have already built what I need for U0 and this vertex. Now, let's see what we can do starting from these two vertices to the remaining ones. Okay, so I have 2, I have 7, I have 4, I have 8, or I have from U0 1 plus 2, 1 plus 7, 1 plus 3. Okay, and that's all. I don't want to go back to U0. Do you see what I mean? Somebody does not understand what I'm talking about? Yeah, sure. Always, please stop me. It's a recursive thing. Of course, you start with U0, and you must take in one by one all vertices. And each time you take one vertex in, it is by a shortest path. Okay? But how can we do that? Initialize the system. U0 is taken in, its distance from itself is 0. Okay, trivial if you want. Now, whenever you have taken in a set of vertices, look how you can build a shortest path from U0 to one of the remaining vertices, possibly by passing through the vertices which you have already taken in. Example, in this case. Second. The first is U0. Second step, let's look at what is around, and precisely the ones which are adjacent to U0, meaning there is an edge from U0 to them. And you have just 5 of them, okay? This with weight, let's call it length, okay? With length 1, length 2, length 7, length 4, length 8. What is the shortest? Length 1. So I take this vertex in, and I write there a label saying what is the distance from that vertex to the important vertex, U0. Okay. Now I want to build, remember, always shortest path from U0, and I can do that in 2 ways. Either directly from U0 with one edge, or passing through that other edge. So let's examine all these possibilities. Possibilities with just one step from U0. I have length 2, I have length 7, length 4, length 8, just from U0. Otherwise, let's see whether I can get shortest paths passing through that one. But I have 1 plus 2, 1 plus 3, and 1 plus 7. These are always greater than 2. 1 plus 2 is the shortest, but it is longer than just by going directly through this edge. And that's exactly what we do, to take in that vertex, but with this edge, not this path, with this edge. And so this has distance 2. Okay? So now, let's see. I start again from U0. What do I have? 7, 4, 8. Let's go through this one. 1 plus 3, which means 4. Plus 2 I don't need because this one is already in. Okay? 1 plus 7. And going through this, 2 plus 1. Okay? And 2 plus 5. So 2 plus 1, if I write down all these things, I recall 7, 4, 8, 4, 3. I have a length 3 if I go like this, okay? And so, I don't remember if it's down or above. Yeah, it's here. So this is the next I take in. And this is at distance 3, okay? There are other paths from U0 to this vertex, but they are longer. For instance, 1 plus 3, it is 4. 7 plus 3, it's 10. Okay, but if I go like this, then it is 3. And I can easily compute that because I've written down this label which tells me what's the distance from that particular vertex to the king. Okay, U0 is the king and we are starting from it. And so I take in also this, and label is 3. And now, again, what do we have? 4, 4, 7, 1 plus 7, 8, sorry. Oh, no, yes. This is 8, okay, and this is 4, okay. So 7, 4, 8, 8 by going like this, and 3 plus 6, 9, or 3 plus 3, which is 6, okay. So of all these numbers which I just said, I think 4 is the least one, okay. So I'll add this one, I guess. And actually it's what I had, okay. And so here is, I see, I put label 4, which is the distance from U0. The more I go, the less I have to count, actually. Why? Because I have less and less vertices to take in. Tell me. From U0 to all the others. Okay. In the navigator, they have tricks to avoid things which go all the other way. It's interesting, very interesting. If you want to do something commercially useful, which computes quickly, but the base algorithm is this, okay? So now I just have these 3 left, okay? So let's see how we can reach the 3 ones which are left from here. Directly 7, directly 8, going through this, it's 4 plus 6, 10, or going through this, which is 3 plus 6, 9, okay, and or going here, which is 7 in this way, or 3 plus 3, which is 6, okay, and so 6 is the smallest of the numbers which I've just said. And so I take exactly this one. So I thicken up this edge, and I put the distance 6, which is here. So you see, it's shorter to go this way than directly through this way, which is 7. You might ask, is that true? How is it possible that it's shorter to go through different ways than directly through one way? I said that this might be thought of as length. It's not like that. Maybe you have different weights according to the moment of the day, and you have rush hours, and this in this particular moment, this is actually shorter maybe, but with a terrible traffic, okay, and so your weights are not Euclidean distances, but are times to travel, okay? And it might very well be so that it's quickest, fastest to go this strange way than to go directly, okay? Again, are there some Romagnolo people here? People from Romagna? No more. They all gone away. Okay. There are people from Romagna who know a particular type of thing like this, which is called Stradelli Guelfi. Okay. Sure, next, we are just left with these 2. What's the easiest way to the shortest, the optimal way to go from U0 to these 2? So let's see. Here we only have directly 8. Also, there is another possibility with 8, going like this. It's equivalent, because it's again 8, okay? Or we might have, look here, 4 plus 2, okay? I have 4 and 2, which is 6. And so this might be better. Let's see what we need for going here. 4 plus 6, 10. It's more than the 6 we have there. 6 plus 4, 10. It's again more. 3 plus 6, 9. It's more than the 6 we had. And so I guess that the next edge we take is this one. And so it is, okay? And so we have distance 6 for this vertex. And finally, what are the ways from U0 to this vertex? And so I guess it is 3 plus 6, which is 9, or yes, 4 plus 6 is 10, which is more. 6 plus 4 is 10, which is more. And all others are, so this should be the last one to take in. And so it is. And so we have 9. Not only do we have the minimal lengths, but we have also the paths of minimal lengths in this way. But remember, not in general, this is very much vertex-centric. It is the best for U0. It's not the best for connecting everything with everything. Not that in any way we get everything connected with everything, okay? Meaning that if you you're not interested in U0, which is Paris, you can all the same go from Bologna to Copenhagen. You go and make this, and then you go to, okay? And it's not so good for you, but it's because you wanted Air France, okay? Because you have 9 plus 4, so it's 13. You could have 6, but you must take your own aircraft and go 6 from Bologna to Copenhagen. You don't have a personal aircraft, and Air France is the cheapest that you find, okay? Or if you want to go with Ryanair, you must go naked, as you know, okay? And not breathe too hard because they discover. And so you do all this trip, okay? So everything is connected with everything. And this is what, because you get what is called a spanning subgraph, which is a connected spanning subgraph, which reaches all vertices, it is connected, and so you surely have a path from everywhere to everywhere else, okay? All right. And that's all for our first chapter. There are other things in this chapter, but we don't. Oh, yes, that we have. Oh, yeah. I want to do that, which is a very old, it's a medieval puzzle. I don't know whether you have ever heard of this puzzle in your countries, in your, okay? It comes from medieval books of mathematics, so to say. So, okay. So let's see. You have a wolf, a goat, and a cabbage on one bank of a river. We have a ferryman with a boat, but he can take only one of them at a time. Okay, the cabbage must be a big cabbage, actually. Okay, all right. And what's the problem? That there are configurations which are forbidden. The configurations in which you have alone, goat and cabbage, or goat and wolf, okay? If the ferryman is there, it can make sure that nobody eats nothing, but if the ferryman is not there, then you get into troubles, okay? And so there are forbidden configurations. Okay, how can we do that? There is also, the second is also a rather common puzzle, but it's wrong. It's it's wrong to put it here. Maybe you might think, why is it wrong? They didn't realize that it was wrong. But in the new edition, the one which you pay if you want to read, this problem is not here, at least. It's somewhere else. But here it is wrong. Try to see why it is wrong. Anyway, let's take this which is correct in this position. How can we solve this by the use of the of graph theory? Of course, you can do it without graph theory. Okay. Maybe you have solved it as a child. Okay, good for you. But we see here that we have a standard process, which is Dijkstra's algorithm, used in this situation. But we must prepare everything. So let's do it. So I'll put here only admitted situations. So I have the river, okay, and what I have on the two banks. I know that I start with ferryman, wolf, goat, and cabbage, okay? Then let's see what we can have. For instance, can we have wolf and cabbage on one side?
Yes.
Yeah. And ferryman and goat on the other. Can we have let's say wolf, goat, and ferryman here, and cabbage on the other side? Yeah. If the ferryman is there, no terrible things happen. Okay. And also, of course, we can have also the symmetric ones. Then what can we have here? We want to have the symmetrical, that one, of course, which is our goal. We have the symmetrical this. Correct? Do we have something else possible? Ferryman, goat and cabbage, for instance. Ferryman, goat and cabbage, and wolf on the other side, and the symmetric one, wolf here, ferryman, goat and cabbage. Do we have something else? I don't think so.
Yeah, only goat on the next slide.
Pardon me?
Only goat on the next slide.
Oh, yeah, sure, thank you. Yeah, let me put this a bit further. Okay. Okay. Now we put an edge if we have just one step from one situation to another.
So how are you configuring these situations? I mean, how are you deciding that this has, the goat has already passed the bank? According to the condition in question?
According to the fact that the only thing which is forbidden is goat and cabbage by themselves, wolf and a goat by themselves. Okay, so I can also put these and eliminate them because these are not to be considered. I could also put here goat and cabbage, ferryman, and wolf, okay, and it's symmetric, goat and cabbage, and also wolf and goat, ferryman and cabbage, wolf and goat, ferryman and cabbage, but these are not admitted. I don't want to consider them, okay? All right, but is there, if now I want to connect by an edge two situations which can be consecutive with a boat trip, just one boat trip, okay? And so my problem will be, can I get from that situation to this? Okay, and so from here, where can I go with just one trip? The ferryman must be on the right side, okay? So not here, not here. Why? Because it should take two things with him, which is not possible, okay? So surely here, okay, the ferryman can take the goat there, or it can take the so ferryman on the right. It's the only thing which he can take there. Okay. Now from here, with one trip, the ferryman must be on the first bank. Okay. So it cannot go here because either it goes back or it goes to
The one next to it, the one next to it. Yes.
It just goes ferryman, wolf, and cabbage. Ferryman, wolf, and cabbage. This one, correct?
Yes.
And then nothing more, because he has to be on the left bank, and the only other possibility is to go back to the initial solution, initial situation, which is of no interest. Okay. Now we can see from here. What do we have from here? Ferryman on the left, ferryman on the right, with just the cabbages. No, it's not possible because it's a forbidden one. Okay, it could be, but he would be a silly man going from here to here. Okay,
the ferryman should take the wolf next, because
I don't want to see what's next. I just want which connections I can do. Okay, or we can also we have already seen from here. We don't have any other possibility, for instance. Let's examine this one. Later, next we'll find a walk, okay? Maybe an optimal one, a path, an optimal path. But for the moment, let's just complete the graph which we have. So I examine this, and so if the ferryman takes goes alone, you would have cabbage and goat on the left, which is this one, which is forbidden. So we don't even connect them. Okay, where was I? Here. So the ferryman can take, for instance, the goat to the right. So goat, cabbage, and ferryman. Okay. Or else he can take the wolf on to the right and leave the goat. So this, correct? Am I correct? Okay. Okay, let's see this one. So this one, the ferryman cannot go to the right, leaving goat and cabbage.
So
It is
I have a question regarding the question. I mean, it says that he can only take one of them at a time. Just one of
just one of the.
Then how are we transporting two of them? Like wolf or cabbage?
No, we are not transporting. This is what we are doing. Each trip is of the ferryman either alone or with just one object. Can you see? From here to here, ferryman and goat. From here to here, ferryman alone.
Yes.
This is how we connect. Okay? Are you with me?
What about the next two conditions?
These ones?
Yes.
Ferryman going with the goat.
And
No, cabbage is already there.
How is that possible? Because the question says cabbage, goat, and wolf are on one bank of the river.
We are here.
Yeah.
Okay, and we want to go here.
Yeah.
Now, let's split the problem into two problems. First, jot down the graph of possible trips. And then let's use Dijkstra's algorithm through that graph. But our edges are one admitted trip. One admitted trip is two conditions. You don't leave goat and cabbage alone. You don't leave wolf and goat alone. And the difference between the two conditions are that the ferryman either has traveled alone or he has traveled with just one object. Okay, so for instance, how can we go from here to here? Because the cabbage is already on the right bank, okay? And the ferryman takes the goat to the right bank. So it is correct. Going with just one object, cabbage was already there. Okay, and this is admitted because we have goat and cabbage, but the ferryman is there to avoid troubles. Are you with me? And again here, what do we have? Ferryman takes the wolf to the right bank, where the cabbage already was. And the goat is left on the... Okay. So now here, what can we have? Ferryman going alone? No, because you would leave goat and cabbage alone. And so that's not admitted. You could take, a ferryman could take goat to the right. So we would have cabbage on the left, ferryman, goat, and wolf.
The upper
right beside it.
Here. Okay. Am I correct? Yes. Ferryman takes goat to the right. Yes. Okay. Or conversely, ferryman is here with wolf and goat and takes the goat to the left bank. Okay. This is important. These are all reversible. Okay. And after that, so ferryman takes goat or ferryman takes cabbage. So this one, correct? Yes. All right. Nothing more from here. Okay, yes, because ferryman goes no. Okay. Let's see here. Ferryman takes to the right, goes along to the right. Okay. Ferryman takes the wolf to the right, and so on the right, on the left, we have a cabbage alone. Yeah. Okay. Or ferryman takes the cabbage on the right, and so wolf is left alone. correct? Okay? And ferryman, yes, ferryman goes alone, that's the only other possibility. Now, what about this situation? We can have that this it comes or goes to ferryman and goat on the left, ferryman and goat to the left, and that's all, okay? And that's all because ferryman cannot go alone. Leaving a goat, wolf and cabbage, it's a horrible thing happens. The goat is eating the cabbage and the wolf eats the goat. Terrible. The ferryman can take the goat to the left, okay? The ferryman takes the wolf to the left, no, leaving cabbage and goat. It takes the cabbage, no, because it leaves goat and wolf. So the only connection is this. Now here.
That one.
Pardon me?
G on the left side connect to the previous one.
Yes, we have to do something yet, I guess. We have to see this to what it is. It can be connected. Ferryman can. So what have we seen so far? Ferryman can take the wolf to the left, already done. Ferryman can take the cabbage to the left, already done. Ferryman can go alone. This means this connection. Okay? Correct? Sorry, I do it a bit better.
Would you please write a number under each circle?
Pardon me?
Would you please write a number under each circle?
Not now. The number on each edge is just one for the moment, okay? It's the length, it is one.
No, I don't
What?
mean that. I mean, actually, you can see the circle. It would be much easier to understand which two circles are connected. For example, we can tell you connect 4 to 6. It means
Okay, but do you need, we are almost at the end. So I prefer to see exactly what is inside, what is on both banks. But, so now, this is the last connection we could do for this one, okay? As for this, it was ferryman and goat to the left, ferryman and cabbage to the left, and we cannot have anything more because the other possibility would be ferryman alone, but he would leave a cabbage and a goat, okay? So no more connections out of this. Here, possible connection from ferryman cannot go alone leaving wolf and goat. Ferryman can take the goat to the left, okay? Ferryman can take the wolf to the left. So the graph is we have everything, okay? Now let's start. This is our beginning, and so we are distance 0. Now here we are, there is only this, and so we are at distance 1, okay? Now, no problem. This is distance 2, okay? No problem from here. Only possibility is this, okay? Now let's see what we can have. We have that, okay, this we have already, we have these two at distance 3, all right? Okay, and then what happens? Now from distance 2 we don't have anything more. From distance 3 we have, for instance, that we can go here, yeah, and so this is distance 4, and also from here to here this is distance 4, correct?
Yes.
And now we are left with this and this. Let's see. From here we also have, distance here. So this one is at distance 5, correct?
Yes.
Because there is no shorter path. Yes, the only two are distance 4, so this is distance 5, and this is distance 6, and finally this is distance 7. And so we find a solution, which is this, then this. We have more than one solution, and then we go, for instance, here, and then here, and then here, and finally here. This is one solution. There is another one going through this particular vertex. Any questions? Okay. I take a picture. It will be, I build the PDF with the blackboards. Okay, if you want to take a picture, no problem, but just know that I take a picture and put it in a PDF. I've seen that some of you have, all of the ones who are not attending, I have just visited those videos which I've made. Okay. Nothing more here in this chapter. Then I just give you the first few things of the next chapter, which will be the subject of the next lecture. But since we have 7 minutes, I want you to have a glimpse at what we are doing next time. Please give me the correct definition. I stick very much to definitions. I have my good reasons for being so obsessed by definitions, okay? So please remember, if your professor has an obsession for the time of the exam, that must be your obsession. He is crazy, you have to be crazy. He is silly, you have to be silly. After the exam, you do whatever you want, okay? Now, so please stick to the definitions. What is a tree? A tree is a connected acyclic graph. What's the meaning of connected? We know just from the previous hour. Acyclic means a graph which contains no cycles. So a tree is a connected acyclic graph. If you start with something which is not the correct definition, you start in a bad way, okay? Both things have to be considered. Now you have some theorems which are rather easy, and these are the ones I'll tackle next time. In a tree, any two vertices are connected by a unique path. This is very important for the idea of connectedness, because it means that you have an optimality, a minimality, in the sense that if you connect vertices of a graph by a subset which is a tree, you are minimizing in the sense that you are not putting something superfluous in your subgraph, okay? So, for instance, you will see that what we have got by Dijkstra's algorithm is always a tree. meaning it is connected and it contains no cycles. And also, I can say it contains all vertices of the graph, so it is what is called a spanning tree. Okay, so it's a minimal way of connecting together all vertices of the graph, of a connected graph. Okay, if you have a spanning tree, you can have several spanning trees, and we'll have one also in Kruskal algorithm at the end of this chapter. Another nice thing is that you have a fixed relation between the number of vertices and the number of edges in a tree, which is the number of edges is exactly one less than the number of vertices. And I want you to be able to prove this easy theorem by induction and not by an example. I can also give you an example next time to show you what it means, what we are doing. But the reasoning must be done in a completely general way. And then we have some consequences, and we have very many properties of this particular graphs. Trees are very important, and very important in particular in the organization of a database. And the M3, a particular tree, is what Dijkstra and Patella did to become famous in all the world of people interested in search engines. Okay, so trees are very important. But for the moment, we stop here. Okay. Any questions before I close the recording? Okay. So see you next time. Ciao.